In this tutorial, we will look at a heat and mass balance for a single effect evaporator. Let's look at the schematic. So we have the various streams going into the evaporator, the vapors leaving on the top. We have steam coming on the side, the feed entering at the bottom, and the condensate leaving the system along with the concentrated product. Note that the tubes and the heating chest of this evaporator is called calandria. Now let's conduct a mass balance. So for the feed, we have m dot f, which is the mass flow rate of the dilute feed in kilograms per second. We have m dot s, the mass flow rate of steam, as kilograms per second. We have m dot v as the mass flow rate of vapors exiting the evaporator in kilograms per second. We have m dot p, the mass flow rate of concentrated product in kilograms per second. And we also have the solid fraction in the feed as xf, which will be dimensionless. Similarly, the solid fraction in the concentrated product is denoted by xp, which will be dimensionless. So we can write the mass balance by looking at what is entering the system and what is exiting the system. So we have the feed entering the system, and the mass flow rate is m dot f, and that equals the mass flow rate of vapors leaving the system, and m dot p, the mass flow rate of concentrated product leaving the system. Note that in the evaporator, steam and feed remain separated because this is an indirect way of heating. When steam condenses, it leaves the evaporator as a condensate. So steam does not mix with the feed, therefore we do not include the mass flow rate terms for either the steam or the condensate in the mass balance. When we look at the solids balance, we note that xf is the solid fraction in the feed, and it is dimensionless. So xf times m dot f will represent the amount of solids in the feed, and that will equal xp, which is the solid fraction in the concentrated product, which is dimensionless, times the mass flow rate of the product. And that will represent the amount of solids present in the concentrated product stream. So that is our equation 2. Now for the enthalpy balance, we write m dot f times hf, where hf is the enthalpy of the entering feed in kilojoules per kilogram. We also have enthalpy entering into the system with steam. So we have m dot s, the mass flow rate of steam, times HVS, where HVS is the enthalpy of saturated vapor at temperature Ts, that is the saturation temperature of steam, and the units will be kilojoules per kilogram. So the heat is entering this system either with the feed or with steam. This is the only two ways that heat is entering this system. And that equals the heat leaving with the vapors, that is m dot v times HV1, where HV1 is the enthalpy of saturated vapors at temperature T1. T1 is the boiling point inside the evaporator that is maintained by certain vacuum conditions. The units for HV1 are kilojoules per kilogram. So in addition to the heat leaving with the vapors, we also have heat leaving with concentrated product stream, and that will be denoted by m dot p times HP1, where HP1 is the enthalpy of concentrated product stream in kilojoules per kilogram. We also have heat leaving this system with the condensate. This is the condensate that formed on the outside of the tubes as steam condensed into condensate. And the enthalpy content will be m dot s, that is the mass flow rate of the steam, times HCS, which is the enthalpy of the condensate in kilojoules per kilogram. Again, note that the heating is done in an indirect manner, so all the mass of the steam entering this heating chamber leaves as condensate after it condenses into liquid water. So the mass flow rate of the steam, m dot s, is the same as the mass flow rate of the condensate as we see on our schematic. So let's see how we can determine each term in our enthalpy balance. So we have the enthalpy of the entering stream, HF, equals CPF, which is the specific heat of the feed, times TF, which is the temperature of the feed, minus 0 degrees C. We base all our calculations for enthalpy with a reference temperature of 0 degrees C. Note that enthalpy is always relative rather than absolute value. So HF then, the units will be kilojoules per kilogram, since we have the specific heat multiplied by the temperature. We are going to assume that we are using saturated steam, then HVS is obtained from steam tables depending upon the saturation pressure or saturation temperature of the steam. HV1 is obtained also from the steam tables as enthalpy of saturated vapors at temperature T1. HP1 is the enthalpy of the concentrated product stream. So we use the specific heat of the concentrated product, CPP, and multiply that with T1, where T1 is the temperature maintained inside the evaporator, minus 0 degrees C, where 0 degrees C, of course, is the reference temperature. HCS is obtained from steam tables as enthalpy of saturated liquid at temperature Ts. Now we are going to assume that the condensate leaves the evaporator at temperature Ts. If the condensate leaves at a lower temperature than Ts, then we will need to determine that additional sensible heat leaving with the condensate. The area for heat transfer in the calandria can be obtained with the following equation. Q, the rate of heat transfer across the tubes, will equal U times A times Ts minus T1 equals m dot s HVS minus m dot s HCS, where U is the overall heat transfer coefficient in watts per square meter Kelvin. A is the area in square meters, and of course Q is the rate of heat transfer in watts. So this equation can be used to determine the area required to accomplish a certain amount of heat transfer for concentrating liquid feed. The performance of the evaporator is expressed using a term called steam economy, which equals m dot v divided by m dot s, where m dot v is the mass flow rate of vapors and m dot s is the mass flow rate of steam entering the evaporator. A typical value of steam economy for a single effect evaporator is close to 1.